Lecture 7, Part 2, Normal Distributions. The standard normal distribution. This is the most important distribution that we'll be working with in our class. So let's first talk about the characteristics of the distribution. First, the distribution is bell-shaped and has a single peak at the center, so it's perfectly symmetrical. Second, it's symmetrical around the mean. Third, it's asymptotic, which means the curve gets closer and closer to the x-axis, but never actually touches it. So basically the tails extend indefinitely in both directions. We can think of this as a statement like anything is possible, right? Anything can happen far from the center of the distribution, but as you move further and further away, those incidents become less and less likely. The location of the distribution is determined by the mean, mu, and the dispersion is determined by the standard deviation, sigma. The mean, median, mode are all equal, and the total area under the curve is equal to 1 or 100%. Here's just a quick look at the normal distribution. You can see here it's perfectly symmetrical, and you can see the tails of the distribution here. And what we want to know is, again, that the tails extend indefinitely to either side of the distribution. The normal distribution is a family of distributions, meaning that wherever the mean is, that distribution will shift to that mean. Now, the one that we are most interested in is going to be the mean, the normal distribution, where the mean is always equal to 0. So the standard normal distribution. Converting a normal distribution, which can be of any mean or any standard deviation, into a standardized normal distribution takes a few steps. So the standard normal distribution that we're going to be using pretty much throughout our course has a mean of 0 and is called the Z distribution. So Z is basically what we think of as how many standard deviations is some value x from the center. So a Z value is a sign difference between a selected value designated x and the population mean divided by the standard deviation. So this is how we take a value x and convert it into how far that x value is in terms of standard deviations from the mean. And we're going to call this Z. So again, the Z-score basically tells you how many standard deviations a given observation is from the mean. So the Z-score itself helps us understand relative standing, which is basically a measure of where we lie relative to the rest of the distribution. So let's look at an example. John scores 80 points on both his math exam and English exam. The math exam has a mean of 70 and a standard deviation of 10. So just by looking at this mean, what we notice is that he scored a little bit below the average in this. He scored a little bit above the average in this case. In the English exam, he got a mean of 85. And in this case, we can see that his score of 80 is slightly below the 85 average. But here the standard deviation is 5. So let's see how he ranks in terms of Z-scores. So for his math test, he got 80, the average was 70, and the standard deviation is 10. So he was one standard deviation above the mean in the class. So he did well on his math test. In his English class, his Z-score was 80 minus 85 over 5. He was one standard deviation below the mean, and therefore he actually in fact did worse in his English class than he did in his math class. So in this case, your actual score doesn't matter. What matters is how you compare to the mean. Let's talk about our Z-table. So this here, what you're seeing, this is a Z-table that we'll be using in this course. Now, as a very specific guidance here, please never Google Z-table. And the reason is we're using specifically our textbook Z-table that looks to find the area between 0 and some Z value. So there's a few steps to this process. First, go to the row that represents the ones digit and the first digit after the decimal point, the tens digit of your Z value. So if we were looking for 1.96, we'd start by going to 1.9, which is right here. Next, we go to the column that represents the second digits after the decimal, which is the 100th digit. And in this case, it's 0.06. So notice right here we have 1.96, which is what we're looking for, which is the intersection of the row and column from step 1 and 2. The next video will give you a full overview of how we find z-values. The standard normal distribution, also known as the z-distribution. So the z-distribution is used when we have continuous data that is symmetrical in the way it is distributed. So when we're thinking about our normal distribution, think of our bell-shaped curve, as you may have seen before. So first, the way we find area here is just like we discussed in the CDF and PDF, and the uniform distribution is area is found using a region of values that we're looking for. So first thing first, let's point out a few key details. If we look at this distribution and we imagine that the tails expand to infinity on either side of the distribution, there's a few things that we want to get comfortable with. First, if I took this distribution and cut it into exactly half, right, put a line right in the middle, what I know is that the area on the right side of the distribution is equal to 0.5, or we can write it as 50%. The same thing applies for the left side of the distribution. We know that the total area on the left side of the distribution is also equal to 0.5, or 50%. So basically, if we imagine this distribution with the mean in the center, the mean being 0 standard deviations away from the mean, what we know is if we were interested in finding something, an answer to a question like this: what is the probability that a value, a random continuous variable in this distribution, is greater than or equal to the mean, okay, of the distribution. So basically, if we look at the distribution, here's the mean of the distribution, and if we're looking for an area greater than the mean, well, that's the 50% or 0.5 area greater than the mean. Now, for all other different values, we're going to start looking at what's called the z-distribution. Let's have a look at the z-table. This is the z-table that is assigned to you in the textbook. With the z-table, you'll notice a few things. Now, be careful. Don't Google z-table. Okay, use the one in the textbook and or the one I will upload into Brightspace in this section. You should see it attached in this specific module. Now the reason is that the z-table can be read different ways, and sometimes it's organized in slightly different ways. The z-table that we're going to be using for this class is shown this way. It gives us the areas as such. If I have a normal distribution, here's our mean of that distribution, okay? The z-table here in the textbook gives us an area between the mean and some z-value. So let's say, we'll say this is some positive z-value. So the table is always showing you an area between some z or some standard deviation greater than or less than the mean, okay? And you'll see, in fact, if we look at the picture here of this distribution, you'll notice right at the top, there's a picture showing you exactly what I described. So you'll see that the z-table is showing you area between 0 and some z-value. Okay, so let's do a few examples and we'll work through a few different renditions of reading this distribution. Here are a few examples we'll work through. Let's start with example A, we'll call this. Here we're looking to find the area between 0 and 1.2. So we're looking for that blue shaded region. Now this is basically asking us this question. What is the probability of randomly selecting an object that is between 0 standard deviations from the mean and 1.2 standard deviations from the mean? So what do we do there? Well, first we've observed this number, the 1.2. So now we go to our z-table. And here on the z-table, what we'll notice is a few things. First, you'll have this column with the z-values, and the z-values are going to be the first two digits. So basically, if we look at a z-value of 1.0, that's basically telling us that we're looking for the area between 0 standard deviations from the mean and 1 standard deviation from the mean. If we go to z of 2, that's basically telling you the area between 0 standard deviations from the mean and 2 standard deviations from the mean. In this specific example, we're looking for 1.2 standard deviations. So in that case, here we have 1.2, which is shown right there. And with that case, we'll see 1.2, and it'll give us this area here, which is 0.3849. So in any distribution that is normally distributed, the area between 0 and 1.2 standard deviations from the mean is 0.3849 or 38.49. Another way we can think of this is this way. The probability of randomly selecting a continuous variable that is between 0 and 1.2 standard deviations from the mean is 38.49%. Let's look at part B. So part B is interested in finding the area between 0 and negative 2.25 standard deviations from the mean. So let's first look for 2.25. So first, let's look for 2.2. So 2.2 is right here. That's 2.2 standard deviations from the mean. Now we're looking for the 0.05. So that will be here, right? This upper first row is going to give us the hundredths place of our z-score. So the area there is basically 2.25 or 0.4878. So the area between 0 and negative 2.25 is 0.4878 or 48.78%. Notice something I did, right? Notice this was a negative here. Negative and positive doesn't matter in this case because we're looking at area, right? The area itself can't be negative. Area is always positive. Z is just movement away from the center. Okay, we'll illustrate an example of this in class. But basically, if we are looking at taking steps, let's say we're on a number line and we start here at 0.0. If you take 2 steps in this direction, 1, 2, right, you took 2 steps. Right? That's the distance traveled. Now, if you traveled the same size 2 steps to the left, you still travel 2 steps. Right? It doesn't matter which direction you went, the amount of travel was the same. And you can think of this as exactly the same as the area when we're thinking about our normal distribution. Okay, let's do a few other examples. So let's look at example C. Looking for the area between negative 0.05 and 1.5 standard deviations from the mean. First thing I'm going to do is I'm just going to put a little dotted line here at 0 because we're going to need to calculate 2 areas here. First, let's start with this area between 0 and 0.5. So this little red shaded region. So let's go here to 0.5. Right? We can see that that area is equal to 0.1915. So this area is 0.1915. Now for the area between 0 and 1.5, so this area here, now for that we're going to go to 1.5 here on our z table. So here's 1.5. Okay, and this tells us that the area is 0.4332. So this is 0.4332. So now what is the total area between negative 0.5 and positive 1.5 standard deviations from the mean? Why, we simply just add the 2 components and we get 0.6247. Okay, so the probability of randomly selecting a continuous variable between negative 0.05 and 1.5 standard deviations of the mean is going to be 62.47%. Okay, let's do our last example here. In this case, we're looking for the area greater than 2 standard deviations from the mean. Okay, so we're looking for the area greater than 2 standard deviations from the mean. Notice how small this region is, right? Notice it's going to be a small region. So first thing we're going to do is we have to do this in 2 parts. The first thing we need to find is what is the area between 0 and 2 standard deviations from the mean. So let's find that first. So here is 2 standard deviations from the mean, and that area is 0.4772, almost 50%, right? So here is 0.4772. So in order for us to find out what's here in the tail of this distribution, well, what do we know from before? We know that the entire area on the right side of the distribution of the mean is exactly equal to 0.5. It's half the data. So the total area is 0.5, and the area between 0 and 2 standard deviations is 0.4772. Then that means the area greater than 2 must be 0.5 minus 0.4772, which equals 0.0228. So once we found the z-values and the areas, let's look through a specification of the steps to find our z-value and the probability of a certain outcome. Step 1, convert your raw data point into a z-value. Step 2, draw the distribution. Step 3, shade the area that you're looking for. And finally, step 4, find the area of your variables of interest. Here's an example I will solve for you in a video coming up in the next slide. So example, coffee temperature. So have a second, pause this video, write these down, and get ready to work through the problem on the next slide. Example, coffee temperature. The temperature of coffee sold at Coffee Bean follows a normal probability distribution with a mean of 150 degrees and a standard deviation of 5. Our first question is, what is the probability that the coffee temperature you get from the coffee you purchase is going to be between 150 and 154 degrees? So let's follow our 4-step process to get our answer. Let's start with step 1. Step 1 takes our random variables or raw data points and converts them into z-values. So first things first, let's convert 150 into a z-score. Recall that the z-score of any value is equal to x, which is that value, minus the mean of the distribution, which in this case happens to be 150, and we divide it by the standard deviation, which is 5. In this case, we have a value of 0 because 150 is also the mean. So we're going to be looking for an area between 0 and some value. Now, second part is we need to find the z for 154, and that's going to be 154 minus 150 divided by 5, which is equal to 0.8 or positive 0.8. So that's step 1. Step 2. Now we draw the distribution. So first we have our line. Here's our normal distribution. What we found here is that the mean of 150 in raw data is the same as a mean of 0 in standard deviations. What we also found is that 154 is also equal to 0.8 standard deviations above the mean. Now the area we're looking for in this case, our step 3, shading our region that we're looking for. So the shading is going to be our step 3, and we're looking to find that area. So first we have our z-table here below. Now we're going to be looking for 0.8 on the z-table. And if we look for 0.8, we find it right here, and we find the area of 0.2881. So this region, step 4, this region is equal to 0.2881. So what question does this answer? Well, it answers the question, what is the probability that the coffee temperature is between 150 and 154 degrees? And that's going to be equal to 0.2881 or 28.81%. Okay, let's go on to question 2 and follow the same steps. So here we're looking for coffee. What is the probability that the coffee is more than 164 degrees? So first thing we do is we're going to transform this. Okay, so first we're looking for the probability that x is greater than or equal to 164 degrees. Okay, so let's convert the x into a z. So the z of 164 is going to be 164 minus 150 divided by our standard deviation of 5, which gives us a z-score of 2.8. So now, second step, let me rewrite this into a z statement, the probability statement. So in terms of x values, we're looking for x being greater than or equal to 164. Now in terms of z values, we're looking for the area greater than or equal to 2.8. Okay, step 2, let's draw it out. So here's our distribution. The mean of our distribution is 150, which is equivalent to our 0 in terms of the standardized format. Here we're looking at 164, which is 2.8 in our standardized format. So what are we looking for here? We're looking for the area greater than 2.8. So we're looking for the tail, right? We can see this is going to be a fairly small area, but let's find exactly what it is. First thing we will do is we will look up the area between the mean and 2.8, so 0 and 2.8. So let's find 2.8, and 2.8 on our z-table is right here, and that's equal to 0.4974. So going back to our distribution, this area is 0.4974, but we're looking for this area here in the tail. So in this case, right, our last step is going to take our total area on the right side of the distribution, which is between 0 and infinity, which is equal to 0.5, and subtract the area between 0 and 2.8, which is 0.4974, and that's going to equal 0.0026. So the probability that you get a coffee from Coffee Bean that is greater than or equal to 2.8 standard deviations above the mean is going to be 0.26% of the time. Or we can state it this way. What is the probability that the coffee temperature is more than 164? That would be also equal to 0.26%. So very unlikely. Third question, what is the probability that coffee is at most 160 degrees? So first here we're looking for the probability that x is less than or equal to 160 degrees. So let's transform that into a z-score. So z of 160 is equal to 160 minus 150 divided by 5. So we get 10 over 5, which is 2. So we're looking for the probability that the z is less than or equal to 2. So step 2, let's draw our distribution. So here's 0, which is equal to our 150. And here is 160, which is 2 standard deviations above. Now notice here we're looking for the entire area less than 2. So that includes not only just the region between 0 and 2, that includes everything on the left side of the distribution. So how are we going to find this area? Well, first in the z-table, we're going to look up the area between 0 and 2. And what we already know is that the area in the entire left tail of the distribution is equal to 0.5. And then we're going to combine them together. So what is the area between 0 and 2? We find that that's equal to 0.4772. So 0.4772. So what is the probability that z is less than or equal to 2? Or what is the probability that your coffee temperature is less than or equal to 160 degrees? Well, that's going to be 0.5 plus 0.4772, which equals 0.9772, or 97.72%. Press pause in the video and see if you can solve this problem. Here we have a mean of 27 miles per gallon and a standard deviation 1.6. Try to work through solving these 3 questions and we will answer these in our class. That's the end of Lecture 7, Part 2.